Good evening, I am Mr. Ish. I think perhaps more interesting than anything, even more so than the sine x and the cosine x derivative derivations, is that of the tan x. We know derivative of tan x is equal to secant square x. With that, I welcome you to this video. Thank you for watching this video. Before you start this derivation, you know we always have to look at things within this format. Limit as h approaches 0. We use a basic definition of a derivative to come at this derivation procedure for whatever function we're looking at. When we're looking here at tan x, and tan x is going to play very well into this part right here, tan x plus h. Coming into this, you'll have to know this trigonometric identity. Tan x plus y, or tan x plus h, is equal to tan x plus tan h. This is something you'll have to remember because it's going to come into play, divided by 1 minus tan x and tan h. Very well, as you remember from the trigonometry classes, tan x plus y was tan x plus tan y divided by 1 minus tan x tan y. Except here, instead of using y, we're using h. So keep in mind this and this is what we need to come to that outcome that we want. Okay, this actual limit derivation procedure for the tan x derivative is slightly lengthy and slightly complicated. There would be a reason for many students to just shy away from it and just learn tan x derivative as secant square x. But in this video, I want to show you this derivation procedure, and I promise you it'll be worth your time. You have this template laid out for you, and we just continue from right here. When we open it up, I showed you what it gives out. Tan x plus tan h. I showed you that at the beginning of this video. Tan x plus tan h over 1 minus tan x tan h. We have this minus tan x still in the numerator. We'll put an over 1 over here, and we have all of this over h. We have to do a common denominator here in the numerator, and it will be work, but it'll be worth it. We have 1 minus tan x tan h as our common denominator. This goes in that common denominator one time. It multiplies with everything here on the numerator. On that side, you have tan x plus tan h. We have a minus sign over here, and then we have a tan x, and we'll put that. This one goes in this that many times, and then multiply with this. We'll have 1 minus tan x tan h. And I think my handwriting is getting a little sloppy over here. Anyhow, let's not forget this h. When this is h, it's an over 1. You can flip it around and bring it right here with this common denominator, and very well it will attach with that. There's nothing wrong with that, and it's legitimate. Limit as h approaches 0. We open up that numerator expression. We have tan x plus tan h. Now I'll try to keep my handwriting good. We'll open up that expression, and with the parentheses, you have tan x plus tan square x tan h all over h times 1 minus tan x tan h. It's lengthy procedure, difficult, and I believe that is the reason why people just ignore it. They just remember the derivative. I don't think there's anything wrong with that, but knowing how to do this derivation procedure can and it will set you apart. What can we do over here? Tan x minus and positive cancel out. I have a tan h over here, and I have this item here. From these two items here under this bracket, I can separate a tan h. I won't write the formality of the limit h approaching 0. I'll just skip that. I'm putting a tan h over here, and I'm isolating it from these bracketed portions. I have a 1 plus tan square x all over everything you see right here. I've done nothing here which is not allowed. Everything is just algebraic manipulation. Tan x tan h. Think about it. I've opened up this parentheses. I cancel out the tan x. I looked and saw this part right here and this, and there's a commonality. Tan h tan h. I isolated the tan h. 1 plus tan square x is what I get. You know 1 plus tan square x is a trigonometric identity. Tan square plus 1 is equal to secant square x, right? And we can use that. We can bring a secant square x right over there. What do we get now? We have limit as h approaches 0. Now I'm going to space things out a little bit. Why? Because I'll tell you momentarily. I have a tan h, and I'm putting this multiplying sign. I have this identity which equals this secant square x. Remember that. Tan square x plus 1 equals secant square x. Sine square x plus cosine square x is equal to 1. Cotan square x plus 1 is equal to cosecant square x. These are the three trigonometric Pythagorean identities. I just utilized one and I made a substitution, and this is what I have. Now, under this tan h, I'm bringing this h. Under this secant square x, I'm bringing all of this. 1 minus tan x tan h. Alright, now look what we do over here. We bring in the properties of limits, the product property of limits. Limit as h approaches 0, all of this is multiplying with that. We can even do this, right? This limit is multiplying with that limit. If you were to evaluate just this specific limit over here, if you were to do a graphic derivation of a tan, tan looks like this. If you were to do that graphic derivative procedure, you know how it is. You pick the specific x values and you map the tangent lines that generate. When you do that, you end up getting a curve which looks something like this, and that is a curve of a secant square x. That's how you can do a tan x function giving rise to secant square x derivative. Alright, you can do that and use that as a bailout measure. The bailout measure comes right over here. If you were to put 0 right here in place of h's, you'll get a 0 over 0, an indeterminate limit form, and I'm only looking at this first part. When you know you have an indeterminate limit form, you can use a L'Hopital's rule. You do the derivative of the numerator and you do derivative of the denominator with respect to h, all of that. When I am utilizing that graphic procedure of derivation, I know tan h will become secant square h. Alright, it will become that. Because the graph is that of a secant square, not a secant but a secant square over 1, for which you can put 0. When you put 0 here in places of h, you know secant square of 0 is the same thing as 1 over cosine of 0, which is 1 over 1. All of this equals 1. Everything here in this initial parentheses by means of this L'Hopital's procedure will come out as 1. And I can very easily put 1 right over here, representing this part here. Now let's examine the second part. The second part, you can put 0 here in places of h. When you put 0 in places of h, what happens? It doesn't affect the numerator by any means because there's an x, not an h. You have 1 minus tan of x times tan of 0, which is a 0. 1 minus 0 is a 1. You have secant square x over 1, which is equal to secant square x. So that just comes out here as a secant square x. And now, with that having been determined, we have 1 times secant square x is equal to secant square x, and the derivation or the proof procedure has been completed. If this seems a little complicated, we'll verbalize it again. You start with this basic template, you know it and you've seen it. It brings in this trigonometric identity, tan x plus y or tan x plus h gives you this. And of course you have this, you work it out through the numerator with a common denominator. I just married here the h with this denominator because you can do it. You open up that entire common numerator you have over there and things cancel out and you can see things which isolate. When you isolate the tan h, you have a trigonometric Pythagorean identity come out. Tan square x plus 1 equals secant square x, where you can substitute secant square x over there. I isolated everything over here. And these are the bubbles I used to isolate. Here was one bubble and here's the other bubble. And I isolated them under their individual limits utilizing the product of limits. Remember, a limit property, the limit of a product is equal to the individual product of their limits. And that's the property I'm utilizing. You separate them out. This part requires a L'Hopital's rule because you have an indeterminate limit form come into play 0 over 0. We know tan h is equal to secant square x by means of a graphic derivation procedure of the derivative. All of this zeroes out in terms of the limit form, but when you do the derivative, you get a secant square h over 1. You put 0 in there, you get a 1. This boils down to a 1, which is right here. This, by means of substitution of a 0, only zeroes this out. You have secant square x over 1, which is equal to secant square x. You take it through and you're done. Secant square x. Remember, before we wrap this video up, we were looking here at the derivative derivation for a tan x, alright? For a trigonometric function and not for a hyperbolic by any means. It could have been helpful had I parenthesized these so we wouldn't be giving the appearance of hyperbolics coming into play. We can spend like a few seconds here and just do some of this parenthesizing. It will very well clear the air. Because you can see in some instances where we have tan h, it could look like a hyperbolic tan, but that's not the case. Everything here is trigonometric. We're not looking at hyperbolics by any means in this video. Now you can see clearly the picture is complete, the derivation is complete. Trigonometric derivation here for a tan derivative giving rise to secant square x. Keep this in your mind, in your back burner. If you want to understand or learn this, you can. You may never be tested on it, but it would be something useful if you could do. Thank you for watching. Stay tuned. Have a nice day. Bye.